it's very possible that whenever I begin to factor a given problem, I'm going to have to use multiple methods that we've talked about in the same problem. So we're going to go through and look at 3 examples where I have to use multiple factoring methods in order to fully factor the given problem. So for the first problem, I start out with 12x squared minus 2x minus 30. And it should always be my gut instinct to look for GCF first, because GCF reduces my problem down and makes life easier for me. So I look at this and I see the 12, the negative 2 and the negative 30, and realize that I can go ahead and pull out a 2 from all of those pieces and nothing more. And that leaves me with 6x squared minus x minus 15 on the inside. So I got from my first step to my second step with GCF. It simplified my problem. Now I look at the inside, this trinomial that's still left, and see if I can factor him using any methods. In this case, it's going to be a is not equal to 1. So I go ahead and run through that whole process. Remember, I find factors of AC that add up to b. So in this case, AC would be 6 times negative 15, which is negative 90. And I want to find factors that add up to b, which is negative 1. So I look at it and I realize that I'm going to use 9 and 10 as my 2 numbers, with the 10 being the negative, because I want a negative 1 when I add them together. So I'm going to leave this 2 chillaxing out front and not forget about him. I'll come back and get him later, and continue on with this process of a is not equal to 1. So I keep the 6x squared. I split up negative 1x into negative 10x plus 9x, and then I keep the negative 15. From here on out, I just want to keep using GCF, so I split it in half and use GCF on each of these small pieces. From the first piece, I can pull out a 2 and an x and be left with 3x minus 5. My goal is to get a 3x minus 5 out of the next piece so I can keep going. So if I pull out a 3, I am going to get a 3x minus 5. Remember, the key to using GCF is getting the same binomial in both of my halves. Because if I look at this, split down the middle still, I'm allowed to yank that 3x minus 5 out front, and then I have 2x plus 3 left, which completes the a is not equal to 1 process. But you can't forget, I still had a GCF out front that I have to bring down in order to complete my problem. So my final answer is 2 times 3x minus 5 times 2x plus 3. Without any one of those pieces, it would not FOIL out to my original problem. For my second example, I'm going to look at the following binomial: 12x squared minus 27. And when I see a binomial, I automatically think difference of squares. But in this case, I'm going to have a little bit of problem, because 12 is not a perfect square, and 27 is not a perfect square. So I can't start with difference of squares. But that's okay, because I can always start with GCF. So I look here at 12 and negative 27, and I realize I can pull a 3 out from each of them, which is going to leave me with 4x squared minus 9. So again, GCF comes in handy as the first step to simplify my problem. Then I look at the inside, and I realize right here that now I have difference of squares. So I go backwards, and I pick out those conjugates that I FOILed out in order to get that binomial. One's a plus, one's a minus. I get a 4x squared using a 2x and a 2x. I use a 3 and a 3 in order to get the 9. And again, do not forget the GCF that's chilling out front. You have to drop him down in front in order to get my final answer. There's 3 pieces to my final answer: a constant out front, and then my set of conjugates. And if I FOIL those all out, I would get back to my original. Our final example is going to be another set of binomials. So 16x to the 4th minus 81. When I look at this, I do have binomials, so I start thinking difference of squares, and I realize that 16, x to the 4th, and 81 are all perfect squares. So I set up my conjugates with a plus and a minus, and I think what gives me 16x to the 4th? Well, I need a 4 and I need an x squared in each of the beginning places. The 4's give me the 16, the x squareds will give me the x to the 4th. What gives me an 81? Well, having a 9 and having a 9. So I get these conjugates right here, and a lot of people like to stop at this step and say, okay, I got from the first step to the second step using difference of squares, and I'm done. And that's right if you're looking at just the first piece. That piece is fully factored. There's nothing more I can do. There's no such thing as a sum of squares. But if I look at the second piece, I actually go ahead and do difference of squares again, because I have perfect squares and I have the subtraction to give me the difference. So when I take this and I break him down again into these smaller parts, I get conjugates, plus and minus. To get the 4x squared, there's a 2x and a 3 for the 9. So a 2x and a 3 for the 9 again. And don't forget that this piece is still part of my problem, the 4x squared plus 9. So I have to bring him down. So 4x squared plus 9 out front. So the answer to this problem actually has 3 binomials instead of just 2 binomials or a constant out front. So this is difference of squares wrapped up in difference of squares. Traditionally, we use GCF first to simplify the problem, and then a second method, but sometimes we'll use difference of squares twice, like we did right here.